So this is 6.1, the beta lesson, and we're going to focus on measuring the spread. Variability are synonymous. So you have the standard deviation, and the heading of the book is, in parentheses, and variance. Let's make sure we understand what variance is. Variance is a measure of variability. Also, measure of spread. It really is not, you're not going to use it until higher level stack courses, but you're accountable for what it is. And it's the value of the standard deviation before you take the square root. That's all variance. Right? So, the variance, if it's discrete, see this sigma? Two things. First off, when you see a Greek letter, that goes with the population parameter. When you see a Roman letter, that goes with the sample statistic. So this is a Greek letter. That's a small case sigma. Sigma squared is saying the sigma is the standard deviation. It's a measure of, right? We look on the calculator, here's what this is saying. All right, so I have this data in here. I don't remember. I guess we did this last week. And I go stat, calc, one variable statistics, list one, list two. This is from the alpha lesson. You notice what you're getting here? This is sigma, the small case sigmas, what's on the PDF. This is the step. Measure spread, it's in there. The sample standard deviation is empty. The S, the Roman letter, is empty because in that scenario, we took list two, we added up, we got 1. So if the sum of the probabilities is 1, then we don't have a sample. We have all the data. There's no point in getting a sample statistic. Okay? So this sigma on the calculator output corresponds, when you do the one variable statistics, or anywhere you find that in the stat menu. If I go here, second quit, bars, 5, which you're not used to seeing, but bars 5. Every time you run something statistically, it gets stored there. So you go back and harvest it. It stays there until you do something else. But if you look right here they are again, S. So this is going to give you the sample standard deviation of the last data set you took. 4, sigma, the population standard deviation. So if you want this step, what are you doing? You're finding out how far each data point is from the center. So I have x sub 1, first data point. Subtract mu sub x. Use a Greek letter. That's the center of your population because you have all the data. So the list 2 is going to add up to 1. That's why we're using mu here instead of x bar. How far they are? Well, all of those are going to add to 0 because they're all going to balance to the mean. Make sense? If you add it up, how far do they use to the mean? You get a 0. Because the negatives would work against the positives. And so that we don't have to deal with that, we square it. Multiply it by the likelihood of that event. And then what? X sub 2 times mu times p sub 2 happening, all the way to the last entry. That's what you're getting for the variance. When you take the square root of the variance, you end up with a standard deviation. So you'll see that when we do a problem. and we go to 13 and 25. And then continuous, when we told you the difference between continuous and discrete is you can take on values between the integers. This is continuous. The analogy is that clock right there, that second hand, is discrete. It's pausing between the seconds. If you've seen clocks where the hand is sweeping. You won't see either one in the new building, they're all digital clocks. So they're all over. So we're going to pause this, and you're going to go to two problems, 13 and 25. We're 13. Ready? Well, what is the step and what does it mean? So the center is 1935. That's how much money he brings in doing this on average. Add or subtract it typically varies by about $6.43 from there. So what happens? So we look here and we say, here's the distribution. This is from when we loaded the calculator on the alpha lesson. We said, okay, if we just go here, stat, calc, one variable statistics, list 1 and list 2, it's giving us that value. But how is it getting it? It's getting it by doing this. Here's the algorithm. Now, this would be helpful for you to do. If you don't have the data in your calculator from the alpha lesson, or you didn't need it for the problem, then load up that data. I'm going to go up here and I'm going to type at the top of list 3. I'm going to put second one. In fact, I'm going to put it in parentheses. Parentheses. Second one, subtract 1935. Now, if you didn't know what it was, you could put in the mean. Yes? 1935. We're going to square it. The reason we're squaring it is because if we added them up, they would come to 0. We push enter. Right? We get those values. We're going to multiply those values times the probability. The probability is in list 2. So I go over here, and I go to the top of list 4 and say second 3, what I just got, times list 2. Now what? We're going to go to the home screen. Second quit. Second stat. Math. Find the sum of what? Of list 4. That is your variance. The variance does not have applications in our course. However, you can get a multiple choice question where they ask you for the variance. And if you're not, tuned into this, you're kind of drifting through it, the standard deviation would be one of the incorrect choices. All you're accountable for is what that is. So I have to go here and take the square root of the answer. Now what? Well, last time we did this, that value was stored where? Here. second, bars, not second, bars 5, it's in 4. So that's in there until you type over it. So if I just type 4, brings you to the home screen, there's the value. So doing it the long way is not something you're going to have to do. But being able to do it the long way is going to confirm you know what's happening and how to use the algorithm. Yeah.
I know there's some of them
Well, 4 itself is the product of each of the probabilities times squared values. How far the use of the mean squared times the probability. It's just a step in the middle of the calculation. So 25. Right? And we have this uniform distribution for 25. And all this is, right? The easiest way to do this is imagine what happened. This graph has got a base of 5, and it's been slid 1 to the left. Make sense? That makes it a little more confusing than it needs to be. You can slide it back where it was from 0 to 5, and then just do a translation of 1 for all your answers. So what's happened? If the base is 5, the area under there has to be 1. So the height of that thing has to be 1/5. Has to be 2/10. Then what? How much is between -1 and 1? Which means what? That the class got dismissed a minute early to a minute late. Somewhere in that interval. You do not have to worry about what happens if they got dismissed right on the minute. The line has no dimension. So what are you doing? The width of this thing is 2, from -1 to 1. 2 out of what? Well, the whole thing's 5. That's counting 40% of the graph. 40% of the time, the class will be dismissed. Within 1 minute, I'll be scheduled time. Because when you get to college, there's no bells. That's good. You don't feel like you're being ordered around. But it's bad in some way, because some teachers just keep going. What is the center of the distribution? Well, what's dead center? Well, dead center from 0 to 5 would be 2.5. And when the whole graph got slid 1 to the left, it'd be 1.5. So the expected outcome is you're getting dismissed 1.5 minutes late. Okay? And then C asks, find the value that makes this statement true. The probability is greater than 0.25. Later than, the probability is a quarter. If you think about a box plot, here's a symmetric box plot. Does that mean 2 2500s in each quartile? So this problem in context of the box plot saying we're here. To the right of that, right? The probability that y is greater than k, later than the third quartile. So every quartile is worth 1/4 of the width, 1/4 of 5. So it's 1.25. If I go 1.25 from the 4, we get 2.75, which is 2.75 minutes, which means a quarter of the time you're dismissed 2 minutes and 45 seconds later. Okay? So that's it for 6-1 beta.